Hi, I am AHMED Hanif and the title of my project is Sustainable Material Management in the United States, and in particular the Municipal Solid Waste Effects and Figures. In this introduction slide, we will talk about what sustainable material management is, what methods are available, what the aims are, and who is responsible for that. Let's talk about the sustainable material management first, which is a systematic approach that is used to serve human needs by reuse of available resources most productively and sustainably throughout their life cycles. The method begins with resources attraction, then goes on to the use of various resources, and eventually to material recycling or product disposal. The sustainable material management strategy seeks to minimize the amount of products used in product life cycle while also reducing the environmental effects of its use. The U.S. Environmental Protection Agency is responsible to protect the environment by implying the efficient waste management policies. Sustainable material management units in various countries around the world have specific focus on sustainable material management because it relates to waste management issues, with an emphasis on waste use in particular. In different countries, sustainable material management is also responsible for enabling economic productivity and better social consideration. In the United States, sustainable material management practice is in line with the government efforts to protect the environment, as this task is assigned to the Environmental Protection Agency, which assists in the sustainable material management process in resolving waste management issues. Despite the Environmental Protection Agency is trying their best to protect the environment, there are concerns related to waste management as well as economic growth, which we will see in the coming slides. The United States is grappling with a major waste disposal issue, particularly in urban areas. Waste management has become a significant environmental concern because excessive waste disposal results in waste accumulation, which is harming the environment. Many materials are going landfills directly due to non-availability of material disposal, advanced techniques of reuse and recycle, and no alternative options are available. Most landfills are on the verge of closure due to overcrowding and necessitating facility expansion or demanding new landfill constructions. Every day, Americans are likely to generate more than 2 kilograms of waste, plus the construction waste, which the figure is not known yet. This means that more waste is generated while there are no good plans or policies in place to manage waste disposal in a way that is both environmentally sound and beneficial to the economy. Hence, it is very important to research about this problem since it helps to determine how waste disposal impacts the economy, as well as we will know the value of using other waste management options such as recycling various products to prevent waste disposal into the environment. While conducting my project research, I've gone through two articles which is published. One is published by Zagoswitsky in 2011 and second one published in TICO by 2020. According to TICO, which is published in 2020, who has explained that economic value of waste management in terms of work creation and tax income generation for the government. From this, waste management creates a major source of job opportunities in the United States. According to this study, the United States produces about 12% of global municipal solid waste per year. Changes in modern American lifestyle have influenced the significant rise in waste generation since the 1960s. According to this research, there would be approximately 12,000 waste management company providers in the United States by the end of 2021. Over 200,000 Americans have already worked for these companies. As per the second article, Zagoswitsky published in 2011, who assessed past waste management practices and present waste disposal practices and found out that the waste disposal practices for both periods in the United States were different. He conducted the interviews and analysis that in the past, homeowners generated small quantity of waste and were solely responsible for waste disposal, while over the time, it has changed to weekly garbage pickup at doorsteps, with the wastage being disposed of in the neighborhood landfill site before being burned openly. Waste landfill sites and open garbage burning were identified as a major source of health problem in communities due to solid waste disposal practices. This study brought up a problem of inequity in a solid waste management in the communities. According to the finding in both these articles, The management strategies should include promoting educational campaigns that raise community awareness about waste reduction, product reuse, and solid waste recycling. The purpose of this project research is to gain a deeper understanding on waste generation and recycling trend for coming years' quantities so that a better waste management planning can be done in advance as well as better waste management practices can be implemented. In addition, this analysis aims to increase our understanding of the importance of recycling role to the nation's economy overall and what areas US Department of Environment should focus on for improvement and for immediate change in certain waste policies. As a mean of mitigating waste disposal problems in the United States, it is also important to understand potential situations in terms of materials that are likely to be produced or recycled. The following two datasets were used in this analysis. First, the waste management data, which was given by the United States Environmental Protection Agency. The datasets provide details on waste disposal, including tonnage estimates from 1960 to 2018. The information in the dataset depicts the amount of materials generated, recycled, combusted, and other materials disposed of in landfills. The values illustrated in this dataset are for a broad selection of items and goods related to urban waste stream sources. The second dataset was economic importance data, which was gathered manually from the Recycling Economic Information Study, which was published in 2020. There were no much data available, so we have created this data manually from this article. The created dataset provides details on how various materials have influenced jobs, how much checks they provided for the economy, and how much wage the goods have generated in terms of billions of dollars. This is the brief summary of both the datasets, how the datasets which we analyzed, what it includes. The waste management dataset includes the different material products names in the first column. Then different columns include different quantities of material like the generated quantities, the recycled quantities, the combusted quantities, and landfill quantities. And then finally the time periods starting from 1960 to 2018 showing the quantities in tons. And for the second data related to economic importance, the first column was having a different materials names, then the second column were having a number of jobs provided, then the third column was having the tax amount paid, and the fourth column were having the wages amount generated. In this analysis, there are two tools which we have used as can be seen in the below table, which were chosen due to their capability of handling voluminous and unstructured datasets. First, we use Matplot library for the visualizations, and then we use NumPy library for the mathematical computations. Matplot library was chosen because it is highly compatible with Python and it enables us the creation of both interactive and statistic plots. While on the other hand, NumPy package was chosen because it allows for scientific mathematical computations in Python, especially when making the predictions. For the prediction analysis in this research, two machine learning models were chosen. For the prediction, the autoregressive integrated moving average model and decision tree regressive models were first selected. When the accuracy of the models were compared after getting the results, the decision tree regressive model was found to be less accurate. Hence, we relied on ARIMA model for the prediction. This is the first model used for the prediction, which is called autoregressive integrated moving average, and short name is ARIMA model. This ARIMA model was used in this study to forecast the possible future predictions regarding the quantities of produced and recycled materials. This model was selected because in all the models comparing with other, this model produces more accurate predictions. And it is one of the most powerful and simple machine learning algorithms for performing time series predictions. The following steps were taken during this prediction process. First, we identify the trends in data using rolling mean. Then the data transformation was done using log values. Then testing the data stationary has done. Then the data decomposition was done. Then calculating correlation ACF and PACF was done. The ACF stands for autocorrelation function, while PACF stands for partial autocorrection functions. By looking at these functions, a plot of different series, we can tentatively identify the numbers of autoregression and moving average that are needed for further predictions. And second last, we try to fit it the model, and then the results of the predictions has been shown. The trends discovered by the data visualization are shown in the following four charts. The following four charts belong to the trends related to the generated material, recycled material, combusted materials, and the landfill materials. First, we will talk about the chart in front of us, which is related to the generated waste material trends. As we can see on the horizontal axis, it's shown the number of years from 1960 to 2018, and on the vertical axis, it is showing the materials weightage in tons from 0 to 3 ton. As we can see, from the pivot table indicates that from 1960 to 2018, the pattern for the generation of various materials have been increasing, suggesting a steady shift in material output. In 1960, only 0.8 tons of material were made, relative to the more recent years such as 2018, when about 2.5 billion tons of materials were produced. This chart shows the recycled waste material trends. The result from the pivot table indicates that only minor quantities of material are recycled after they are produced and injected into the community. In 1960, only 0.025 billion tons were recycled, as comparing to the recent year where 1.4 billion tons of material were recycled only. If we compare with the material generation, which was shown in the previous graph, comparing with the recent year, in 2018, approximately 2.8 billion tons of material and products were generated in the United States, while just 1.4 tons of material were recycled by waste management companies as business, which means that nearly half of the goods produced are either disposed or either combusted, landfilled. This poses the issue of environmental significance, since the majority of capitals are diverted towards the creation of new products. This chart shows the combusted waste material trends that from 1960 to 2018. This indicates the material combustion rates have been steady and increasing slightly from 1990. More than 3 billion tons were combusted in 2018 only, which is the highest. This chart shows the landfill waste material trends. The result from the pivot table indicates that starting from 1960, only 0.8 billion ton material were landfilled, and starting from 1990, which was almost the peak, around 1.4 billion has been landfilled, and in the recent year 2018, almost also 1.4 billion tons of material has been landfilled. This indicates the material landfilling rates have been steadily increasing over time, and most of the used products ending up being landfilled rather than recycling. For the model evaluation, various testing techniques were used to assess the ARIMA model efficiency in forecasting potential quantities of both produced and recycled materials. Before using the model to get the forecast, the dataset was placed through a sequence of steps. Number first was data transformation using rolling statistics, which included transforming the values of produced and recycled material amounts. Then the Dickey-Fuller analysis was done, which was to estimate produce and recycle data rolling statistics and test data stationary. Then seasonal decomposition was done to remove seasonality, pattern, and residuals. Then the plotting for autocorrelation functions and partial autocorrelation function was done, and then finally model fitting and testing was done through scaling back to the original values. Following the data transformation, it was critical to perform Dickey-Fuller analysis to estimate produce and recycle data role statistics and test data stationary. The Dickey-Fuller finding demonstrate, as can be seen on the screen, the table, that the two datasets were stationary and ready for use in the final model estimation. After getting the Dickey-Fuller model results, the data was then decomposed to remove seasonality, patterns, and residuals. As can be seen in the top four rows, the chart shows the trend seasonality, which demonstrate the data repeating short-term loop. Then in the third and fourth row, we can see the residual plots, which demonstrate that the decomposition was effective in distinguish noise from the linear pattern in the data series. Then the bottom four figures, which display the autocorrelation function and partial autocorrelation function effects of the produce and recycle materials amounts using the AROMA model. These plots demonstrate how well the time series currents produced and recycled quantities values are linked to their past quantity. Below four models it can be seen from this model that the model was functioning properly. In this model fitting testing, we can see the two results. The left chart shows for the generated quantities and the right chart shows for the recycled quantities. The result in this section indicate that the model was well fitted within the data, with the recycled quantities models having a higher accuracy than the produced quantities models. While testing the final model accuracy prior to forecast, it was discovered that the model was able to scale back and read the initial base values of the data, enabling for an accurate future forecast of the quantities. The model performance accuracy was high, since it was possible to read the first 5 rows of the created data series as shown in the figure above. From our analysis, we got the final prediction for the next 14 years of generated quantities. As can be seen in the chart, the red line represents the predicted quantities versus the blue line represents the known quantities. The bottom side of the chart represents the number of years and the left side of the chart shown the number of materials in tons. What we conclude from this future predict generation chart that the future generated material volumes are likely to persist as the population and number of years rise from 6 to 14. Approximately 2.75 billion tons of material are likely to be produced per year from 2026 to 2036 with a high generation rate over that time frame. 13 years from 2021, material generation in the United States will reach a peak point as shown by intersection of the actual and predicted quantities in the graph above. This means that some resources that are used in material generation might have been depleted, hence no more generation. This chart shows the 14-year prediction for the recycled quantities. According to these predictions, as we can see in the chart, by the year 2025, the volume of recycled materials are likely to exceed 0.6 billion tons per year, with this figure expected to rise to about 1 billion tons per year. According to this chart, we can also see that the products that will be recycled in the future will be higher than what has been recycled in the past 14 years. This prediction seems to be right, as more campaigns in the United States call for resource conversion rather than the regeneration of fresh goods products by 2025. This was the second machine learning model type which we used decision tree regression prediction. However, this result did not turn out to be good. The result suggests that the model did not do well in prediction and therefore it was not chosen for further analysis. This is the second part of our project research, which is the economic importance of recycling process. We can see from this waste material economic importance chart, there are three things have shown. At the bottom, we can see the product's name or the items. At the right side of the chart, we can see the tax in billions and wages. And on the left side, we can see the number of jobs it created or it will create. So from this graph, we can see that there is a pre-existing relationship between effective waste management and the economy in general. The blue bar shows the number of jobs, the orange bar shows the tax paid in billion, and the green bar shows the expected wages. There are nearly 680,000 jobs opportunities in the waste management sector, which produces an average of 5.5 billion in taxes. The graph depicts the economic importance of some of the waste material produced and recycled in the United States, with metal goods and C&D appearing to provide more employment opportunities and generate more revenues for the government. This graph shows the comparison between employment and tax correlation, with the number of jobs shown at the bottom and on the left y-axis the text in trillion shows. The graph illustrates the relationship between a jobs as a result of sustainable waste management and the amount of revenue generated by the industry. With less workers in the industry, the country's revenue production will be smaller. With large number of jobs, the tax generated from the sector would be higher. This demonstrates the critical need for improved waste management practices since they have a significant impact on the country economy. This is the summarized conclusions we get from the above analysis. Due to time exceeding limit, we will talk only in summarized way about the conclusion. What we get that majority of the produced goods actually end up being combusted in community landfill sites. Per year, an estimated 1 billion tons of waste are landfills. About 2 billion tons of solid waste gathered from the cities is burned, accounting for about 75% of all generated materials. Waste landfilling spaces have been limited and the current ones are nearly full. This poses significant concerns about the future of solid waste disposal in the community landfill sites, hence it is a significant environmental threat. There is a constructive association between sustainable waste management activities and economic importance. Waste material generates about 5.5 billion in annual revenue and provides about 600,000 job opportunities in coming 14 years. There were following limitations while doing this analysis. The data was unstructured and had to be separated into different parts for use in the model. The selected model was only restricted to the data used in the analysis, with only linear regression models performing best, while the other models were not performing best. There were no enough data available for construction related waste material, due to which we did not include the construction related material or disposal figures in this analysis. There were no data set available related to economic impact figures, and we concluded that manually from the article available. Following are the recommendation after the analysis. There should be development of waste product processing industries to support waste management. The recycling or other environmentally sustainable waste disposal measures should be enforced immediately. There is a need to create awareness on the importance of sustainable waste management in the communities down the line. There is a great need to create awareness of adopting the circular economy models, which has many advantages in waste management comparing with the existing common linear economic models adopted by most industries, especially the construction industries. And that concludes my presentation, and I apologize for taking the longer time than required. Thank you.